Expose a mouse to a high-contrast, flickering grid of a single orientation for 30 minutes, and the visual system begins to adapt. But measuring neurons in the primary visual cortex immediately after that exposure reveals a paradox. Despite the intensity of the experience, there is zero change in firing rate or orientation preference. This chart tracks the firing rates over time. At T0, the line is flat. It takes exactly 6 hours of subsequent sleep for these cortical neurons to exhibit a spike in orientation-specific firing, a process known as OSRP. Depriving the subject of sleep for that same window prevents this change. The trajectory remains flat. The visual cortex fails to adapt. If the cortex is incapable of immediate adaptation, then non-REM sleep must execute a specific set of computations to finalize this plasticity. The visual cortex relies on an offline state to process, transfer, and permanently wire the sensory memories acquired during wakefulness. Here is the visual thalamocortical network. During wakefulness, activity flows through 3 main nodes: the primary visual cortex, the lateral geniculate nucleus, LGN, and the thalamic reticular nucleus, TRN. Form vision begins at the retina, projecting raw data directly into the LGN. For decades, neuroscientists categorized the LGN as a passive relay, believing orientation selectivity was generated exclusively in the cortex. Modern data from mouse models proves otherwise. The LGN contains a significant proportion of orientation-selective cells, driven directly by input from the retina. Look at the node map during the 30-minute waking stimulus. The LGN dynamically shifts its firing responses to favor the orientation of the grid, while the V1 node remains at its baseline state. The initial visual memory is primed and temporarily held subcortically in the thalamus. Transferring that information up to the cortex requires a state transition. The transition to non-REM sleep is driven by a precipitous drop in ascending neuromodulators like acetylcholine. As acetylcholine levels fall, the thalamic relay neurons hyperpolarize. Membrane neurotransmitter receptors deactivate, and the internal voltage precipitously drops. This hyperpolarized state selectively de-inactivates a specific class of ion gate, low-threshold T-type calcium channels. The network stops desynchronized waking chatter. Calcium influx forces the neurons into a burst and pause firing pattern. This rhythm activates the thalamic reticular nucleus. Francis Crick famously hypothesized that the TRN acted as a searchlight, regulating selective sensory attention. During non-REM sleep, the TRN uses its burst firing pattern to generate massive inhibitory signals, known as IPSPs, across the thalamocortical relay neurons. This GABAergic inhibition makes relay neurons refractory to incoming, visually driven excitatory input from the retina. By actively severing the cortex from environmental sensory noise, non-REM sleep creates an isolated environment for internal computation. Isolation is only the first step. The network must now generate coherent rhythms to transfer the primed data from the LGN up to the primary visual cortex. Non-REM sleep features 3 signatures: spindles at 7 to 15 Hz, delta waves at 1 to 4 Hz, and the sub-1 Hz slow oscillation. The slow oscillation is a master pacemaker, grouping the faster rhythms into a single, unified pulse. This synchronization is a physical feat. Layer 6 corticothalamic neurons project back to the thalamus, firing in rhythm with the slow oscillation. This pathway is the essential vehicle for plasticity. Researchers recently used optogenetics to selectively suppress this feedback, specifically during bouts of non-REM sleep. The results were catastrophic for the memory. Coherence between the LGN and the cortex broke down, spindles dampened, and OSRP consolidation was entirely blocked. Corticothalamic feedback orchestrates the thalamic oscillations, physically driving the primed memory from the LGN up into the visual cortex. This mechanistic view challenges the Synaptic Homeostasis Hypothesis, the idea that sleep exists solely to globally downscale all synapses to conserve energy. This theory assumes a uniform suppression of activity, reflecting early models, like those of Ivan Pavlov, which viewed sleep as a state of prolonged cortical inhibition. But the OSRP data reveals a different reality. Visual experience induces long-term potentiation at thalamocortical synapses, proving sleep supports the specific strengthening of connections. This plot tracks the redistribution of cortical firing rates across a sleep period. The x-axis represents the baseline firing rate of individual neurons, and the y-axis shows the change after sleep. Neurons with high baseline activity but low orientation tuning decrease, their firing rates actively depress during sleep. Conversely, sparsely firing, highly orientation-tuned neurons show the opposite effect, increasing their firing rates and shifting orientation preference. Sleep is a precision editor, selectively redistributing firing rates to optimize the visual network signal-to-noise ratio. If the sensory gates are shut, how do non-REM oscillations identify which specific synapses to potentiate? The resonance hypothesis posits that specific neural pathways dynamically synchronize with the overarching rhythmic pulse of the sleeping brain. Neurons that received extra excitatory drive during wakefulness carry an elevated excitability into the sleep state. When the non-REM upstate washes over the cortex, these primed neurons reach an action potential slightly earlier in the oscillation phase than their neighbors. This spike timing order propagates through the circuit, triggering plasticity that selectively wires those early firing connections. Offline vision is an active, coordinated computation, transforming temporary waking impressions into permanently wired visual architecture.